Okay, so it's my pleasure to be chatting with you today about some of our OS research. I think it's particularly an honor to talk to a company that has been committed to the value of operating systems and ensuring that the world around us works because we actually have a solid operating system. So again, hopefully I won't offend you with any of the mistakes I make, but you know, before I really get going though, I should point out that this talk, perhaps a little overly ambitiously, is trying to do two things. One, I'm hoping to give you some sense of how we conduct OS research and why that can be, or the approach to it can be viable and meaningful. But also I'd like to communicate some of our specific research results. So we'll see if we manage to hit that balance or not. This is a 4-hour talk, right, John? Okay, great. So specifically, I'm going to hopefully try to tell you about some of the work that we've been doing in terms of how we can evolve the OS, especially in light of the cloud. But before I really get going, I want to first say that anything that's interesting and good from the things I talk about are all due to the brilliant collaborators and students that I've had the absolute pleasure of working with. With that in mind, I would like to call out especially Aaron Krieger, which many of you may know, who has been my collaborator and supporter since my research career started. And so I really owe a great deal of thanks to Aaron. Now, with that out of the way, there is something I do want to take absolute credit for. Anything that you hear in this talk that sounds crazy or suspect, that is squarely me. So please don't blame them for that. All right. Now, I think when doing research, it's always important to stop and ask yourself, what are we actually doing and working on? To that end, I'd like to start with considering what is an operating system. Now, if we turn to our textbooks, I think what we actually see is a little bit of a disturbing trend. We go back to 1988 and look at Silberschatz and Peterson, we actually get something that is a very, in my opinion, useful, goal-oriented discussion. I want to highlight two aspects from their discussion. Make the computer system convenient to use, and use the computer hardware in an efficient manner. Now, if we fast forward a little bit to 2014, and we look in a book like Anderson and Dahlen, we end up with something much terser and functionality oriented. We end up with manage a computer's resources. Now, actually, if we read on in this book, we'll end up getting a list of functions. Now, of course, as my students would do, no one reads dead textbooks. So let's move forward to the modern world and ask ChatGPT. Now, assuming ChatGPT, and I think in this case it's probably true, is summarizing what it finds, what we end up with is something even more functional in its statement. We end up with actually a list: process management, memory management, file system management, device management, user interface. Now, I think this kind of functional definition is actually part of our problem, as it ossifies our thinking. What we teach and what we study tends to be about the set of things that we have done, and it limits how we think of what we should be working on. So, but with that being said, let's stick with this definition for a moment and use it and ask, does it matter anymore, the OS? Now, in general, of course, I'm very happy for us to entertain a discussion and chatting back and forth. But I will point out, just before I get into these questions, I am posing these a little bit of a straw man, and you can imagine I actually believe the answer is it does matter, but it's not unreasonable to say, well, look, application development and deployment have rapidly become stable. Nobody really depends on the OS interface anymore. After all, so much code is written in Java, Python, JavaScript, WebAssembly, all these managed runtimes whose very goal is to isolate the application from the OS. And for that matter, if we look at modern AI apps actually would really prefer us not to be there at all. All they want is a dedicated GPU, and as far as they're concerned, we should just get out of the way. And from that perspective, perhaps the no OS is the best OS. Then, of course, the cloud. There's just so much hardware out there. Have we reached that point that we can literally just run every app bare metal on a processor in the cloud? And who, again, needs the OS really? So from a researcher's perspective, maybe what we really should be concluding is we're done. The technology has reached stability. And if anything, it's entering maintenance mode, or perhaps even more so, maybe it's even obsoleting itself. And we've played our part. So long, and thanks for all the fish. But I don't think that's exactly the case. I think that we need to, though, unwind and go back to a simpler time, a more progressive time, and assume a definition of the operating system and what role it plays more broadly, specifically as a collection of software that makes it easier to use a computer. And now let me be a little more concrete. I'd like to argue that when I say easier to use, I mean get stuff done. Now, 3 important factors: less effort, less time, and fewer resources. And I believe all 3 matter. Now also, the term computer, as we all know, given how many are probably on us at this moment, is a bit of a vague definition too, right? What actually constitutes a computer? Now I'm going to argue that I want to use the broad kind of definition as the hardware, okay? And broadly defined. And I think taking a more flexible definition like this lets us now explore things in somewhat more progressive manners. Now, I think with this broader definition, it lets us pose 2 questions that I think are interesting to ponder. Now, I think there is no doubt in my mind that Linux, being a well-understood environment that makes it easy to use a computer, is hard to deny. Look, I actually had all kinds of slides in here when I really did think you were willing to sit here for 4 hours with me. That included discussions from the 1970s between professors, and including a polemic by Rob Pike, who sort of says, hey, look, why is there no creativity? But come on, let's not unnecessarily pretend that we always need something new. The truth of the matter is Unix, and therefore Linux, really does provide a stable foundation that many of us use to think about our problems. So I don't think it's an all or nothing thing. So how can we preserve Linux and ensure that we don't actually erode what it's good at? And yet at the same time, look, the truth of the matter is the computer, quote unquote, has changed and will continue to change. How can we evolve the OS in light of foundational changes in the hardware? And I personally believe, as hopefully I'll show you in a minute, that the cloud does represent a change in the hardware too. Now, instead of directly trying to answer those questions right now, I want to actually take a step back and look at, from a research perspective, what have we been doing? Because we, in some sense, have been pursuing aspects of those questions. Now, I know that some of this work is going to seem old when we look at the years, but actually, if we're doing our job right as computer researchers, hopefully we've done things and explored things that now are relevant. Now, specifically, I'm going to go over 4 pieces of work. Let me just give you a quick précis for what I think some of the key things that we learned out of those are. So when we worked on these first three systems that I'll talk about in a minute, one of the core things that we got we got focused on was not building an OS for a machine of a particular size. Rather, was exploring how do you build an operating system that could adapt with the size of the machine. And then I'm going to go on and talk about Libra, which was actually an opportunity to start looking more firmly at how the world could change in an operating system when we didn't have the freedom to just rewrite everything. And then third, I'll look at a project that we call Kitty Hawk, where all of a sudden we got a chance to peer into the future and look at what a data center really could look like. And then finally, before we make a transition to talk about some of the things we're currently doing in the Collaboratory, I will talk about MRT as a capstone to that work where we tie some of these things together. Okay. So Hurricane, Tornado, and K42 were we're a series of operating systems that we worked on spanning the years of 1991 to 2005. Now I want to use a plot here from a 2005 article. On the x-axis is years. Okay? On the y-axis is a sort of generic scale that's being used to plot 2 quantities. One quantity plot in the blue dots is clock speeds of processors released in that year. Okay? Now, what the article also did, actually the source for the graph, it used a trend line to use a projection on where the clock speeds would go. Now, similarly, they took, they plotted here transistors in thousands of transistors, and again, a trend line to help us project the future. Now, this graph was actually updated in 2009, but in the time of the article, it was data up to 2004 and a projection forward. Notice that the years that we did this work, well, I don't know if I can stop, use the laser pointer, but 1991 to 2005. 1991 was the beginning, for those who remember, really the megahertz wars. The mainstream, am I allowed to swear this time? Could give a bleep ass over whether multiprocessors were a thing or not. After all, you were just going to get better computers by paying Intel, or I mean, some company, right? You were just going to double your clock speed, everything would be great, software would get better. But that is exactly the period of time that we were entertaining. What would be the impact of scalable 64-bit, and I'm going to say general purpose mainstream shared memory multiprocessors becoming widely available? Now remember, at the time, any parallel computing was sort of HPC esoteric, right? What we would have read about in our parallel architecture textbook, but seemed to have nothing to do with the mainstream. But we were saying, well, what would happen and what should the OS look like if that became the reality? Notice we end our work 2005. Now, in all fairness, we probably screwed up a little. We probably should have started our work a little later when people would have actually published our papers, but whatever. But the point was that we took a bet, we thought hard, and then we went after it, and we committed ourselves because we felt like it was a reasonable projection. And sometimes that's what you have to do in OS research. Okay, enough of that. So now let me go on to try to highlight a couple of the important takeaways, I think, that we learned from this work. Now, there are plenty of premises, but I'm going to start with the fact that we were building, or at the University of Toronto, and there were other places, OS projects were often paired with hardware projects. And the claim was that we actually know how to build scalable hardware systems out of general purpose processors. To this end, Tornado, that operating system between Hurricane and K42, was in conjunction with a hardware project where we were building shared memory multiprocessors targeting hundreds of processors. And the OS side of the world, Tornado, said, hey, you know something? Look at how that hardware gets scaled. The OS, as a piece of software, if we want this, one kernel binary should automatically adapt to the size of the system it's on. Because the promise of this hardware was going to be that you could call up your vendor, oh, I'd like to double the size of my machine. Oh, I'd like to double it again because I have more work to do. I wanted the OS to scale, right? You didn't want to then say, oh, okay, we'll wait 5 years for a new OS revision to come out. So our suggestion was, this isn't about concurrency control. Look, we all kind of know that if I have a data structure and I protect it with a lock, then it might seem to be perfectly fine when the system has 4 cores in it. What about 16 cores? Now all of a sudden that same data structure and lock becomes contended and is a pain point. So how could we try to figure that problem out? I also want to point out one more thing, which I was trying to imply here. So it's size of the system and number of threads running in the application. Because adaptation for your load as an OS, of course, isn't just about the hardware. You may have spent all that money because you thought you needed that 64-way processor, but in the end, you're running one single-threaded app. Or even 16 single-threaded apps. That's a very different optimization point within the kernel. So we were also after reflecting the concurrent load of the application. Okay, great. Now, there are several things and results, both positive and negative, from that series of work. But I want to focus on the things that sort of drive the rest of the topics we want to talk about and our implications all the way to the cloud computing. So, one, we posited that the way to build this adaptable, scalable operating system was to first start and throw the current approaches away, build a core meta layer to the OS, where it was built out of primitives that then we would program on top of. And in those primitives, we would capture the properties that we felt were critical to reflecting both the application demand and the hardware facilities below us. So again, I can't go into the super big details, but one was that we decomposed the operating system into objects. So at the time, this was kind of a little bit of heresy. We were claiming we were going to write a high-performance OS, C++. But whatever, right? Because what we really felt was that the logical objects that we represent in the kernel, a file, a process, that if we actually used an object to back each of those things, it meant we could ensure that the accesses were to that object and didn't go through metatables. That we would start to reflect the non-shared nature of those objects, of the logical resources to an individual object. Okay. The objects were built out of mechanisms that would really encourage, right from the get-go, that a developer should exploit per core memory in a consistent fashion. The OS developer shouldn't have to think about it. The default is to tend to cause everything to use per core memory. Now, this animation that's been flipping around while I've been babbling is trying to reflect the two things I really want to walk away from. We decided to force the programmer, the kernel developer, to state a policy for how the object should behave when accessed on a new core. So what you're seeing here is this idea that the kernel object, in this case it's a simple counter, is being accessed on a core, and more like a fault-like mechanism triggered the fact that this object has been written to provide a per core representative. And that way, when it was accessed on an unknown number of cores, it grew. Now, of course, we didn't demand that every object look like that. That would have been difficult and a complicated way to get any OS project bootstrapped. Instead, because this was a policy choice, you could just write a version that's not, screw it, just give every processor, point it to the same instance, right? So you could start with just a normal shared instance of a kernel object. But here's the kicker. That's the other thing that we combined with it, was we realized that specialization could be used as a mechanism to bound our complexity. So I think Linux has gone through some of this transition, right? So we know that when a single-threaded application starts up, you don't really want a multi-core representation of a lot of your data structures. You don't need locking. It's unnecessary overhead. As a matter of fact, your unicore performance will go down. A sin that is often committed in academia is we work on scalability, but we show you an inherently bad work for, base case. But when you do real OSs, you can't afford that. The UP performance shouldn't degrade just because you're SMP compliant. But what we had was, notice the word RCU here. So we had actually done our own development of RCU, and that development was used so that we could end up swapping between objects on the fly, which meant we could decompose our complexity. We could write a version of the objects that were tuned for one scenario, and when we detected the need for a different scenario, we could switch. And this taught us the power of specialization. We didn't have to write one Uber implementation for an object, let alone the whole kernel. So I don't have time to go into these performance results, but if folks want to ask me after, we can come back. It was really just a comparison of Linux of the day in 2005 to results we were able to achieve with K42. One thing I just want to point out, this was from scratch, right? This was us starting the OS saying, hey, let's use these aggressive mechanisms. I put all the papers, or at least some of the papers, in the talk so that if you're interested, you can go find them. All right, so now I'd like to move on to Libra. Now, Libra, I think Iran was my manager at the time at IBM. He remembers it differently than I do. But I remember us being tasked with, look, we've got a commercial data center. Stop screwing around with all your shared memory multiprocessors. We want to sell PowerPC blades. We want to demonstrate the value of PowerPC blades. And we want to do this in a standard data center rack. Do something. Okay. So Iran, being a smart manager, wanted to figure out a way that we could work on what we wanted to work on, independent of what we were asked to do. So what we did was build this thing on the right. What this thing on the right is a library operating system. Now, a library operating system, oh, I promised I would stay on this side of the room for the camera. So much for that. The thing on the right is a library operating system that we built by taking just quick little pieces of K42, some of the lowest level components of K42. This was actually a one-year effort, okay? And we took small pieces of K42, glued on top of it a very light POSIX API compliance, and I mean very light. It was only what was necessary to support IBM's commercial J9 Java JVM. We were fortunate enough to be working with the J9 folks, so we had access to their source code. We worked with them to get a build environment so that we could compile the IBM JVM and then, state-of-the-art JVM onto our library operating system. This all runs in one protection domain. Okay? At the time, we were using Xen, so it was a Xen partition. We booted that Xen partition with this OS, and now we could run jar files inside it. We included a high-performance interconnect, but here's the part where things got interesting. To a controlling Linux. Okay, we call that controlling Linux the front end versus the back end. But the real trick, as is often the case, at first I thought it was, oh, look how smart we are. We built this really cool library operating system. But actually, I think much of the secret sauce was not in purely the library operating system. It was in recognizing integration. So what we did was on the front-end Linux, you ran Java, like any other process. And what you got was a proxy process. Now, this isn't just an arbitrary proxy. The proxy had a credential, it had a stood in, it had a stood out, it had file systems it could access. It had all the kind of things that you want to manage an instance of an application. And UPS, you can kill it, which I have always believed is the killer app. Okay? So now, this proxy was a bidirectional proxy. When we wanted the heavy listing, yeah, go run Java code, byte compile it, do it fast, use PowerPC, great. But when we couldn't and didn't want to in 1 year implement lots of stuff, we just asked the proxy to take care of it for us. Use the host OS, the front-end OS, use its TCP/IP stack, use it stood out, stood in. So it became this very interesting hybrid model. And I would argue it taught us that it's not general purpose or special purpose. It's both, and you get this kind of accelerator model. And this was very influential in our thinking. Okay? Neither has to be perfect. And remember that theme? In some sense, this starts to take the pressure off Linux, right? We didn't have to go and beg the kernel to do all the crazy things we wanted to do to support the J9 folks. All right. Here's something, though, that I found very powerful. I'm going to let this animation play, too. Now, what we ended up having was an x86 Linux front end. Okay? And we installed our little kludgy infrastructure. When you ran Java, what actually happened was you would take a Xen partition on a rack or on a group of PowerPC blades, and we would now run. And it looked seamless integration, right? We had architecture heterogeneity, and we had seamless integration to the point that at the time, of course, map or Hadoop was just coming out. And actually, our big goal from our management was make MapReduce better. And so what did we do? As good OS people, we cheated. And we said, look, if we make a Java appear transparent, then all of MapReduce would use our Java, right? And we wouldn't be having all these machines installed everywhere. Instead, Hadoop would just get better. But here's the other thing. Hardware elasticity. In our IBM racks, the demo literally was, we plugged in a whole new set of blades. MapReduce performance went up because all of a sudden more JVMs are being launched on our back end. Also, we could unplug the set of blades, and because MapReduce was written to be resilient to the number of JVMs, performance just went down gracefully. Right? So this was really eye-opening. Oops. This was really eye-opening in terms of what some hybrid OS models could buy us. So I'm just trying to, there we go. Again, there's a paper. Work was done between 2005, 2006, paper published in 2007. Great, so now I'd like to move forward to Kitty Hawk. So in Kitty Hawk, we got a chance to see what was coming. And in a few slides, if you don't believe me, I'll try to give you some evidence why I believe it's still coming. So, you know, it's often said that today's computers are yesterday's supercomputers. We were very fortunate that when we were working at IBM Research, down the hall from us was this ridiculous esoteric group building the Blue Gene supercomputer. And we, of course, being really atypical OS people, not being arrogant at all, we thought to ourselves, we're not touching that esoteric, ridiculous piece of hardware. But it turns out, as is often the case, we were roughly full of it. We were wrong. Because the US government had not wasted the taxpayer's dollar. They had actually demanded that the machine be built out of general purpose processors and support general purpose software development. Because software development is king, right? So we realized that as we started to look at it, it just needed us to go in and add some software to it. We could expose the fact that it was a general purpose system. But from our perspective, what we really learned was that if you don't just cobble together machines with duct tape, which if you ever go visit Stanford and look at the original Google machines, how proud they are of that fact, that doesn't mean that's the right way to do it. Now, if you truly build a machine for the data center to become a computer, we realized, well, what we were taught by our colleagues was, no, this is a different beast altogether. This thing, the number of nodes, to call them computers, processor, RAM, and fabric connectivity, is a system on a chip. Well, the RAM wasn't on the chip, but everything else was, and they were tiny little credit card-like units put into racks. We were now measuring our bootable entities in the quantities of millions. Okay? And, oh, wait, remember that property we were hoping for? The customer's going to call up and they're just going to make their machine bigger? Well, you're straight that the government demanded that of IBM. The national labs should be able to call up and expand their machine. So it had incremental growth built into it. I can't get into the details of how that worked, but it was fascinating. Okay. And that the interconnect does not say, oh, yeah, the big machine, let's put Ethernet in it. No, it was actually interconnects that looked a lot more like buses, but with very intelligent design. Okay? So our question was, hey, how should the operating system evolve on such a system? And it turns out, we realized, no, in that world, now we talk about redefining the OS in a much more radical way. So we wanted, after all, our goal as OS folks, to expose the machine's elasticity and scale that makes it easy to use. Doesn't constrain people what they should do with it, but makes it easy to use. Now, here's the thing. What does software look like when all of a sudden hardware contexts, I mean real hardware contexts, are available to you almost as easy as mallocking and freeing an application? They're like launching and acquiring and deleting threads. Now, our current OSs didn't do that. But that doesn't mean there wasn't a very interesting way to think about this. So we argued that we should first accept that the OS is not one entity. And we claim it's not orchestration platforms that would arise as kings. It's down at the bottom. Build an OS layer that is fast, scalable, has a programmable interface for acquiring and releasing metered units of hardware capacity. Because once you get this big, we are now talking, as a matter of fact, the paper was entitled Global Scale Computer, has impact. You have to accept that people are paying money. You have to make and encourage efficiency. So now the goal was a utility layer, which today we would call an infrastructure as a service layer. And if you squint, you will actually see that ESI in the MOC is very similar. Not only does it have a user interface for an authenticated user to come in and get what we are going to call a communication domain to which they can populate nodes and deallocate them and boot them with OS stacks, it's also programmable. The software inside can invoke that layer of the OS and acquire and release nodes very rapidly. Okay? Now, that means all other software, bootloaders, virtualization, the OS, are really just add-ons. We did not want to claim the right way to do it because, of course, we had our own opinions, right? So this was the funny thing. All of this new stuff and the big lesson I was going to walk away from was, wow, man, Linux really matters. Because it turns out the right way to make this machine available to people, independent of the web interface to get access to it, was actually bootstrapping them with a standard stack that could then get their applications bootstrapped. And then we could stitch in access to the hardware with specialized OSs. Now, I don't have demos baked in for this one, but there's a whole set. There was a URL back there. There's a whole set of cool videos. They're old, but I actually think they're still fascinating. But I do, again, there's papers. But there is something that was interesting to me as a researcher. This was the first time that one of my projects got this much media attention. It was kind of crazy. I got an invite to Stanford, did all kinds of cool things. But here's the real lesson, though. The lesson was that IBM, TD Waterhouse came to IBM and said, we want to see if you can help us beat the benchmarks for ingesting the stock market feeds and do quantitative analysis on them because we see the explosion in automated trading. And so this is going to blow up the rate at which trades are happening, and they're a market mover. They have to stay ahead of the market. Now, IBM had what was something called InfoSphere Stream Computing Platform that they desperately wanted to demonstrate could do it. But they didn't have the hardware. Now, we knew BlueJean had more than enough capacity, both in the interconnect and in processing capability. But InfoSphere was written on Linux. So what did we do? All of a sudden, they heard about Project Geek. All of a sudden, BlueJean became a viable option. We port their stuff. Well, it took no porting really, right? Because it just ran as a Linux app. And then we went in. Went, oh, you don't need to use TCP/IP. Let's just give you a cut through to the RDME fabric, right? So we incrementally won the benchmark by starting with existing software and exposing the hardware to it. Okay, how am I doing for time? Okay. The last piece of work I want to talk about before we start talking a little bit about what we're currently looking at is this thing that we call the Elastic Building Block Runtime, EBRT. So we tried to put together now our synthesis of what was coming. Right? And we said to ourselves, actually, it's really interesting that we believe there will be an opportunity for the OS to expose massive scale and elasticity to applications. And how do we combine what we've learned? Because really, we start to realize for an individual person who owns a slice of this elastic cloud, really they've got a new knob. They can turn a knob up and down based on cost to the size of their machine, right? So clearly, now whether it's network load, you're just talking about some application load on you, right? You ideally want your costs to reflect the actual demand you're under because it's justified. So how could we turn this knob to map? Oh, sorry, I promise I won't break the screen. How do we turn this knob appropriately? And we felt like the software was the real question here. So we went ahead and we took all of our best things that we had learned so far. We took layers of K42 and built a full-blown library OS that could be booted. Now this time it was, the design point was bare metal nodes or VM partitions. And we, at some point, we were still working on Blue Gene and PowerPC, but we abandoned because it turned out that once you become an academic, it's a lot harder to get access to that hardware, and your graduate students would like to actually publish. So now the idea was EverT took that Libre idea but to the next level. The library operating system wasn't just a little command line shell-like environment. Instead, it was a true library, and it had split brain personality. It had one version of the library which could be linked into a Linux application on the front end. The back end library had interconnect with it, and these elastic building blocks were really clustered objects that were capable of growing across cores and nodes. I think the easiest thing is to run a little animation here, rather than trying to say too much. So first off, again, our basic model is that in this elastic context, you're running operating system. One of them is a front-end node, which you log in, it's Linux. Now, for those of you who know it, there's an open source alternative to MATLAB, Maple, and yes, there's Jupyter, but there's another project called Sage. And that was more prevalent at the time, so that's what we built to. Now in Sage, like Jupyter, it has a Python front end. And it really hooks up the back-end libraries, like in Jupyter, NumPy, and so on. So Sage has that too. But now it became really easy. Our library was just a library, right? So we provided a Python binding and a matrix implementation. And now we have a normal Linux front end running a normal process, Sage, but it's linked in to our host side of the library, which has a Python binding that allows the user to instantiate matrices. Now, unlike where it was the entire Java before, now it's down to potentially just one function or data structure being able to enjoy elasticity. So now, when the user does stuff, for instance, instantiates a matrix, randomizes it, but actually, you don't have to instantiate anything for randomization. You only have to serve pieces of randomized values when somebody accesses an element of the matrix. If they access one element of the matrix, then you might get one representative showing. When they do a sum across all the elements, boom, you get all of your representatives. But here was the coolest thing, and it was sort of by accident. Went, oh shit, it worked. Sorry. Python has a garbage collector. And when we reassign the handle to our matrix to another matrix, we did nothing. And boom, all your backend resources disappeared because the garbage collector kicked off the destructor of our object, and all your backend resources went away. So this was fun. But does it actually buy you anything? Complexity, sure. Okay, so here's where the conjectures that a library OS can make a difference. Now, I'm not going to go into these graphs let me just give you some intuition. Again, if we have time and it's not dark, you can ask me questions about the graphs. But if you write an operating system where application code and the OS are really one entity, there's no permissions checking, they're running a single protection domain. As a matter of fact, if you do your job right, application code can be interrupt handlers. You can squeeze so much more, let alone exploiting application-specific policies, like pin all of the memory, like do all kinds of fun things that are custom to your app. So we ended up in the paper, because in academia, it's a lot easier to sell papers, not on integration, but on raw performance numbers. We published a paper demonstrating the value of the OS based on its performance. Okay, there are papers. Oh, I'm sorry, and this was all work by Dan Schatzberg, who was a PhD student. Who's no longer a PhD student, but at Meta. Okay, great. So now, I'm sure I'm way past half, but now I'm kind of done trying to motivate how we evolved our view of the operating system. So now, how have we been building on that? Now remember, you might say, oh, well, shouldn't you just keep doing that? My job as a researcher is sometimes to go, okay, we learned a lot of cool things. Now let's think again, and maybe we were wrong, right? So first, let me just give you some context. This is our kind of worldview, right? Extremely elastic, scalable hardware does become available. We had BlueGene that we first initially played with. The MLC and Cloud Lab represent as best as we can get right now. For us, that layer that would let us stitch and get this hardware was Kitty Hawk. Today, on the MLC, it would be ESI or the Cloud Lab interfaces. We've done a bunch of work to show that we can build library operating systems that actually exploit this to do cool things. But now we really wanted to focus more squarely on what does specialization, because there's this great opportunity, both because of scale and elasticity, to really redefine the OS. Let's explore this specialization. And we're going to explore it along two dimensions. One is what we did to build EBRT really necessary? Do we have to build a from-scratch library OS? And after all, in today's world, dedicating a container, a VM, or hardware to a single app, independent of elasticity, has value, right? Maybe just being able to figure out how to get those optimizations viably in a commodity OS like Linux might be sufficient. So I'll talk about UKL, unikernel Linux, and something called dynamic privilege. And then another thing that we were very curious about, look, in this kind of scale, when we looked at BlueGene, I literally wrote a paper saying that this is global scale impact on the planet. Look around. The data centers are global scale impact on the planet. Being fast is not good enough. Being parsimonious with your resource count and the energy you consume matters. And our job as OS people is to help that efficiency, even when you don't go out of your way to try to achieve it. So then I'm going to talk about our study into, can specialization help with energy efficiency? Okay, so I think I've already sort of said this, right? Our from-scratch library OS is the only way. I just maybe want to point this out. I think everybody probably gets this, but remember, even in today's clouds, no notions of the kind of crazy research stuff. We're already at a point that we're dedicating computers to running a single component of a web service, right? Is there a way to exploit that dedication in some sort of straightforward way that doesn't require like a brand new library operating system? Okay, so this is work by Ali Raza, who's a who also graduated, and this was his thesis work. So is there some way for us to take an application, take the Linux kernel, provide a little surgery, stuff them together, and then will we get something lean and fast, or will we end up with roadkill? So will we get something that will actually service and get us performance advantages, energy advantages, or will we end up with just more complexity and another mess? Okay, so let me at least try to provide a little intuition for what we're claiming. This is our normal Linux process. I think I was editing that on the Uber ride here. Okay, so in the top, we have what the worldview is as we recognize it. We have an address space within the lower half is our process with its dynamic memory, loaded from an ELF file, all good. Upper half is the kernel. Now, UKL asks, well, what happens if we take the kernel, an application, one application, at source code time, compile it, and statically link it such that its code and data now are part of the kernel. So when we run that application, a single instance of it, it becomes what we call the UKL process. It now has the opportunity to start flexing its muscle as privileged software and exploiting the kernel around it to see if it can service its needs. So again, I'm not going to get into huge amounts of detail here, but this is our UKL process, okay? What we want is not to claim, like parity with EBRT yet. What we want to show is a mechanism that would allow an upstream community to make unikernel-like optimizations a thing. So we want to not provide necessarily Uber optimization, but a way of integrating and progressively getting to optimization. So once the application is being compiled into the kernel, our first goal is compatibility. You shouldn't have to work all that hard. Yes, it's a recompilation, but we want some way that effectively just causes every time it interacts with the OS via system call, should just be a function call. So a little bit of glibc magic, and at link time, yes, that can happen. And then we say to ourselves, but we're inside the kernel. A pretty straightforward change that doesn't really require application rewriting is to skip all the standard syscall entry path and find a target interior syscall handler and call that one instead. And then finally is actually go, whoa, I'm inside the kernel here. This is my app. I'm not just taking source code from the internet that somebody else wrote, or I am, and I read the code. I can go in and I can stitch in really weird customization, where I call directly, for instance, to TCP send message. I'm not going to get into how we manage that on a case-by-case basis, but it is all doable. Now, to demonstrate, this isn't some sort of fancy EBRT-like optimization, but it's a pretty straightforward optimization to get if you understand your app. What we show is that if we take Redis, a key value store, this single thing of squishing the application into the address space and calling TCP send message gets us a 26% higher throughput, and tail latency improves by 22% for roughly small effort. Tommy, who's here, would kill me if I didn't at least get to dynamic privilege. So Tommy asked another question. He said, dude, you guys are just full of it. Maybe there's another way to think about this. Maybe the whole problem is not unikernel, library OS. Maybe we've just been thinking about privilege the wrong way. So this is the world that we know, right? User mode, application code. Kernel mode, kernel code, supervisor mode of the hardware. Okay? When we build our kernel code, it's designed and constructed knowing that it's going to run over here. User code, my God, it's not allowed to run there. So it lives in that, and we work really hard never to have a mismatch. The processor's state and the code it's running is always kept very far apart from each other. But if we question this orthodoxy, we might be able to do something quite crazy. For instance, sys libkernel.so. Now, I'm not going to go all the way there in this talk. I'm just going to give you a sense of what Tommy's done. So here's some Python code. Python code running in a good old user process. Except it loads in a Python module that is a binding to a new system call. One new system call called kelement. On return from this system call, lo and behold, we've committed heresy. You are now running user code in supervisor mode. Inside Python, we go read CR3. CR3 is the page table pointer on x86, something that certainly we should not be able to do. So all of a sudden, we can execute privilege instructions. All of a sudden, we've opened up this bottom corner. Now, this actually has deep implications to shipping and thinking about specialization for an application. No longer do you have to turn your head every time to the kernel. You can maintain your personality as a user process and start taking over the hardware, but you can also make use of the kernel as if it were a library. Just quickly, we've done this and demonstrated that this can be done in all our familiar languages. This is a kind of cute example. In Python, we literally copy the IDT into a new piece of memory. We update the IDT and we reinstall it. We literally just remade the world, right, as an application. What we had shown in UKL as being kind of recompile and do all this work, because we can do this at runtime, Tommy actually used the standard dynamic linking tricks and can actually cause that kind of Redis shortcut to actually just be a user tool. So he's got a script that you run it in front of an application and you say, hey, when the PC is this, I want you to call send message instead. And he links in appropriate code. So this, we believe, is a starting point that lets us explore whole new dimensions in what the operating system orthodoxy looks like. Is it worth me going to this, or how far am I over already?
You just hit one. You can keep going. We did let folks know on hop in if they want to ask questions. Now's a good time.
Okay.
We don't have any questions.
Good, because I'm going to keep going. I don't want to hear
Okay. I'll warn you at 1:20 or so just to give you a heads up.
I really do want to tell you about this last area of work, because I think it actually exposes two unique properties of specialization that are critically important once we start realizing our impact as systems people globally. So here's the setup. This is work done by Han Dong. This is also his PhD thesis work. I'm going to actually offer two comments or explorations on specialization here. One that asks the straightforward question. Can these kind of special purpose OSs like FRT, where we've really gone to town, we've really worked hard, can it actually enable less resource consumption, particularly we're measuring energy? And then I'm going to suggest a different view of specialization. Can we actually introduce a new layer to an OS that actually buys us a degree of specialization that's tuned almost to the very load you're on? Oh, sorry, setup. In this case, we're studying network-based applications. That's my hardware. OS application. Our general model is to ask for some application performance metric. What kind of energy do I consume? Okay, this is a very busy set of charts, but let me just tell you, yes, specialization can dramatically improve energy. So first off, there's a really interesting result here. I didn't point it out, but the last time, way back in the talk, yesterday, I told you about FRT, right? So Han, at the time, we were particularly running FRT largely virtualized. Why? Because it turns out that like Linux's investment in all those device drivers is a pain in the butt to recreate in an arbitrary OS. That's part of what makes these library operating systems so unclear whether they're really worth it or not. But in order to conduct the science, Han ported a particular 10 gig Ethernet card to FRT. And now we plot on this very top chart a particular benchmark. It has to do with evaluating an operating system's ability to sustain load onto an application like Memcache-D. And what you're looking for is a characteristic hockey stick curve, which means as you start ramping up load onto the machine, at some point you're going to reach saturation and your latencies, your tail latency on request is going to shoot up. So ideally, on this top chart, you want to move to the right. Okay? So here is Linux is the black curve, and FRT gets double the improvement in tail latency. Okay, so yes, first off, first claim, head-to-head comparison, same piece of the hardware, OS, FRT gets its performance. Hopefully that was going to be true. We were a little surprised that it was as good as it was, but great. Now, what about energy? So it turns out that you can roughly navigate an operating system in the energy landscape by controlling the packet delay in the interrupt card and DBFS. DBFS is kind of an obvious one. Packet delay, we and others have sort of explored that it works as a good control. Okay? Now, on these plots, I am showing you tail latency, and I'm showing you queries per second. The most important aspect is the green dots are Linux, the red are FRT. This is at a low query rate. The blue dot is when Linux is using its default, it's a particular governor and its default algorithm for managing the interrupt delay. So the big thing to walk away is these green and red lines represent what would be called the Pareto optimal frontier. They're the optimal settings. Okay? In all cases, FRT, and as the load goes up, separates from Linux and gets better energy, achieving the same, if not better, performance. Great, so we didn't just burn up the machine just to get our performance. We actually made the machine more efficient. Great. This last set of slides, this happens to be a web server running in Node.js and a couple of network ping pong tests. I just want to give you an example of these black dots. These black dots are us going into FRT and saying, look, we're not a general purpose OS. Screw interrupts altogether. let's just actually make the application pull. It's in control of the NIC. We'll have it pull, but we'll turn the energy way down to pull really slow. Now look, I'm not arguing that's the ideal optimization for every spectrum of uses. But the point is we can, and there are certainly points in the performance space where that can be a win. All of a sudden, because of the library OS, we can explore possibilities that would have been or very difficult to do inside a general purpose OS. Okay, last, I think almost my last core slide too. Almost. We take, now I want to say something else, right? Notice here, I showed you this energy landscape. Well, what we realized was, wait a second. Maybe all those years of digging into the OS and putting all these heuristics all over the place, maybe that's not the right way to think about it. Maybe we should really split the OS up when it comes to control. And then these are very low-level controls. The interrupt delay at the NIC driver queues and DVFS, right? And what we decided is, okay, look. Again, on this chart, these are set queries per second. Different settings of those two things get you different optimality. So what we do is we take a 24-hour Twitter trace, and now a 24-hour Twitter trace isn't nice and pristine, right? It's not at a stable queries per second the whole time, right? It's varying throughout the day. Roughly, it's about every hour, to be honest, because of diurnal patterns on a web service today. So it turns out that if what we do is give control over those two fundamental knobs to a machine learning agent, it turns out that the OS, an entire software stack, is actually a very stable thing. It has optimal sweet spots. And the controller can every so often go in, tickle, and go, oh, you should switch. And when you switch, you get better energy while maintaining performance. So now, in the actual plot, this is FRT, okay? So this blue is Linux default. Energy consumption is on the Y. Time of the benchmark is on the X. The actual request per second is also plotted, but that's less important to us right now. Big thing is, see this distance? FRT wins, but it also adapts when somebody else is controlling. It has no policy in it. Unlike Linux, which has governors and has algorithms, we don't have any algorithms. Our algorithm is effectively, I don't know, I'm too stupid. The ML agent is tuning. But the same ML agent, not a new one, not something that is crazy. If we turn off Linux's defaults and let our control algorithm do it, well, there's a win there too. Now I can't get into all the really interesting science this represents, why it works and why we think this is really interesting. But my main point is that this is now specialization down to the literal instant, right? And we get to throw around the term ML, so it must be good, right? Okay, so where is this taking us? We are now in the process of trying to understand these results in a complex multi-node setting, like in a stream computing environment with Flink. Can we extend it to multiple nodes? The software we dealt with have been, pretty straight up C++ applications that were very friendly. Flink is Java again. So it's got, for 4 worker threads, there's like 98 other threads in the address space that I have no clue what they're doing. The other thing we're doing is we're asking, hey, in the modern world, whether we like it or not, containers are the way that dedicated applications are packaged. What does a containerization do? Do we still get to measure performance and energy in the same way? And can we optimize it? Another one of my graduate students is trying to take this idea of the MLOS and formalize it and build something we call the Shepherd OS. That's designed to extract knowledge that is useful across software stacks and help provide intelligence to adapt and specialize for the in-situ demands. You know, somebody telling me to stand on the right side of the room has almost purposely caused me to stand on the left. I don't know what that says about me or my graduate students. Then the last thing, you might have noticed, those results were with FRT, right? Well, didn't we just entertain 2 projects that were trying to figure out whether we could add unikernel optimizations to Linux? Well, so now we're trying to put our money where our mouth is. Can we get the same wins on that one fixed benchmark on Linux, but using our adaptation frameworks? Okay, so one thing you might have noticed, early on in the talk, I said, good OS researchers, don't we look out? We look way into the future. And yet, everything that I talked about other than the origin point for the work has been roughly narrowing and narrowing and narrowing the time frame it works on. But that's not all we've been doing. We've actually been working since 2004 to explore a radically different approach where neuromorphic or analog devices become a thing on their own. And we can actually really radically rethink how the hardware is going to look. Now, this is partially a joke. There's no way I have time to talk about any of this, so I'm not going to. But I just wanted to point out, we have lots of other things where we're constantly trying to pull. And I think that's one of the roles of research, right? Is to not just do the stuff that's safe that people expect, but do the stuff that's unexpected. And yes, does this mean we might fail? Absolutely. Okay, so I don't think the evolution of hardware stopped. I think from that 1971 article I barely mentioned, it's really worth noting that we both are consumers and influencers of that hardware. I think this idea that Linux is going away anytime soon is full of it. Look, there's such important investments, but we have to work hard not to overburden it, lest it collapse under its own weight. And I think this requires creativity, and it requires us to think about the OS in new ways. And I think this elasticity is coming. So I guess I didn't say this before, right? So number 3 on the top 500 is Microsoft's cloud computer. The number 3 on the supercomputer top 500 is Microsoft's cloud computer. Go look at NVIDIA's Grace Hopper architecture. It looks an awful lot like Lucy. The world will evolve, and I believe that the hardware will move to efficiency points of massive scale. So I think us getting ready and doing work for that matters. I think helping people be frugal. I think there are novel approaches, right? So I don't think the job is done. I do want to thank all those people who have funded us, even when, and despite me, but when it was not obvious. And I'm just going to leave this up while we chat. You know, the game is not over at all. You know, if there's an impact of AI, maybe, the impact of AI is that we're being told chemistry, physics, and material science are going to explode. Do you think computer architecture is going to stand still in the face of those? Not a chance. And are we still going to have to actually run applications? Oh, yeah. So we have a role to play. I think we are reaching the limits of what is sustainable. I think there's fascinating bridges between understanding neurobiology and what we call ML today. And I think that will radically change what the architecture looks like. But maybe more than anything, computation is power. And we, the people who build it and maintain it, we have an obligation to understand the socioeconomic impacts of it. And I think our creativity and integrity that we do real science. We measure things. We don't just speak because it's fun to say, oh, isn't this cool in a marketing brochure? But we actually demonstrate the energy, the performance, the resource consumption. And unfortunately, just writing complex code ain't good enough. Because that maybe ChatGPT can help with. I guess I'm all done. I'm probably like way past.
118. You're good. No questions in the chat, so if you want to open the floor for the room.
Yeah.
Are you back to the slide where we had like the front end Unix operating system and the back end that was the Java sort of optimized one? Sorry.
It's okay.
I love asking the moment, but I don't want to interrupt the flow.
Oh, shit. Sorry.
No, you're good.
There.
You go. So did you find that like the optimizations that you were making for the operating system running like the Java files sort of, because I imagine there was some sort of overhead where you had to interact between your sort of like front end Linux and then like this back end one. So like I assume the overall performance was still like a gain, even though you sort of had to do that proxying like overhead, but the gains from like actually running the Java file sort of offset that.
Yeah, so that's a great question. The question was, well, look, aren't you full of it? Don't you constantly have to go back and forth and pay this extra penalty that you've now added? So two things to that. One, I was being a little coy, right? Like we were running on Zen. And so first off, this control OS, there were actually several of them. Throughout the system, you know I showed the PowerPC and the x86? So yes, some of those were networked, but some of them were beside each other on the same node. Okay? That was a high performance shared memory link between them, so that some of the hard stuff like file system access and so on, we could get quite cheap.
Yeah.
On the other hand, the model was the following, that for things that didn't have the performance advantage you thought, that's where you slowly move more and more into the library OS.
Gotcha.
Right? We took a pretty easy way out.
Yeah.
Right? That being said, there was a couple of very interesting optimizations that came out. And this actually speaks to some of the other work. So it turns out, in such an environment, right, I showed you that big farm of PowerPC blades running the JVMs. All of a sudden, we had privy to hundreds of JVMs, and we had a hook into their application, right? All of a sudden, we could take their string cache. Now, a lot of Java code doing web stuff is parsing strings and converting them, and yet converting them again and again. And the JIT, so the JIT cache and the string cache. So what did we do? CP the string and JIT cache from that guy here, and now just send it to all the other ones as they're coming out. And all of a sudden we got performance win. Not a traditional OS performance win, but a pretty damn cool one.
Yeah.
And actually one that had we gone and tried to micro-optimize something, this win was so much deeper, right? Yeah. Yep. Hey, Mark.
Hey, I have another diagram question.
Yeah.
It's the one about the unified kernel application. It's the application layer and the kernel layer. I saw that and I wanted to ask a question. It's further on.
This one?
No, it's a little further. Sorry.
Oh, UCal.
I think it was, yeah, this one.
Yeah.
Okay, so I see the bottom diagram with the different bits of code and data from both user land and kernel land mixed together, and my security spike sense goes off.
Yeah, you should. As a matter of fact, what's that null pointer dereference going to do for you now? We're going to take the whole damn thing down.
Could you speak to the security implications of this model?
Yeah, there are none. The truth of the matter is, what we are arguing for here is that in the world in which resources are plentiful and you care about your application and you own the operating system, I should be allowed to use the code the way I want. If I am not old enough to know the risk of that, please don't come talk to us. No, look, the truth of the matter is, this is designed to give you an option. It's not designed in any way to argue about that, oh my goodness, this is more secure than sudo. Oh my goodness, this is more secure than putting a module into the system that happens to leak all your secrets. Look, it's specious to argue that security is down to the kernel anymore. Security is down to where you place it. So if this kernel is running carefully architected into a data center application where it's my hardware instance, I might as well be running Apache here, or I guess Apache's too old, a dedicated server, then this is for you, right? As a matter of fact, in some sense, I argue that's exactly why you don't want to get rid of mainstream Linux. There are absolutely environments where we need, like when I SSH in and want to do other things, I want my standard security models. But this app is not privy to those or constrained by those. Was I that overwhelmed?
So you didn't say much about how average programmers are going to be able to take advantage of this, right? You said make it easy,
Sure.
but this is not easy.
This is not easy. Yeah. So I think there again is a spectrum along the research lines. So one thing that we noticed is we do actually fundamentally think that things like the managed runtimes are a great place to hook into. So I think things that we can do to improve below those managed runtimes preserves the managed runtime as the ease. And because we've looked towards having broad swaths even for dynamic privilege that it could integrate in arbitrary applications, meaning that we can partition this kind of functionality into libraries and to user level like tools. Now there's other work that I didn't talk about that extends on that kind of little example I gave about caching the string caches. We actually look at abilities to speed up applications and actually the entire OS without ever impacting the code. So yes, we don't necessarily make a new programming language that makes it easier than it is. I kind of happen to like writing assembly code, so maybe I'm not the best judge of ease, but I happen to believe that one of the big powers of von Neumann architecture opposed to like a GPU is that it presents a relatively straightforward cognitive model to write software to. The question is, can we come up with innovative ways to increase performance and reduce resource consumption while not burdening that further? But
So do you think that in the future, you're kind of going to have pair programming where you have somebody who knows about dynamic privilege and you have an application person and then you say, oh, you did a lot of string copies in there. Let's fix how the string copy thing works and your code will go faster, right? Because that was the cool insight that you came up with to make things go fast, but that's not easy to do.
So I think much like other things, we really think that as the OS, if we start to provide primitives, and this can be a fallacy, right? We start to provide primitives that other folks will use those primitives and package them in sustainable ways. So the question of, do you now go to your JVM writer and say, hey, isn't this cool? And I think Tommy's argued for dynamic privilege because it integrates so well with current libraries that you could imagine ecosystems that develop. Look, ecosystems have already developed around BPF, and that's unfortunate, but it's a thing, right? So I think things that become even easier to use and let you explore the performance space, I think it's about the development of
There's like a guy on the corner who's like, hey, let me tell you about this library.
Yeah, so as a matter of fact, okay, so if we're gonna go there, that was actually the point of Kitty Hawk. The point was that performance, optimizers, virtualizations, everything else, because you're metering and billing usage, yeah, if I've got a bright idea to optimize your stuff, I should be able to sell it on the open market, right? And I should be able to prove to you by actual quantification that it was a win.
I just have a comment.
In that case, I'm just going to get a question first. Yeah.
This is just kind of out of curiosity. With all of the different adaptations that are needed to be done for such a large system, and as we see different optimizations pick up where we need to do things dynamically or dynamically adapt, but it always makes me think of when we hear those types of problems about machine learning and different models of that kind. So do you think there's a big future in the idea of having machine learning doing stuff at the level of determining things within the operating system, or would the overhead for that be too great?
So that's a great question. I am a firm proponent in science. I don't believe arbitrarily machine learning is a panacea. The reason we got it to work is because we did a lot of careful study and then we posed a reasonable problem to learn. Now, maybe, I don't mean to be saying that maybe someday, yeah, maybe we will reach the Uber networks that can do, just look at the world and go, yeah, I can make that computer run faster. Maybe, but for the moment, I think deep knowledge of the architecture, the operating system, and the application, carefully study it, find meaningful opportunities to say, oh, look, Bayesian optimization, that can make a difference there. Oh, a neural network could provide a model, and I could expect that the total cost between the GPU to query the model and what I'm actually trying to optimize and the time frame is reasonable. So I don't think we've left basic science and engineering on the table just yet. Tom, you wanted to make a comment?
I think we've cared so much about Heidi's question about like how easy something is to use and what you get out of it, right? And I think one place where that splits might be like for the system designer, how easy is it for them to prototype and stuff to try, and then for the actual consumer, like the client, like can they just run Java and it just works, right? And like I care a lot about both sides of those, but sometimes it is just hard for the systems person, right? And like, so I love that as a core tension between ease of development, prototyping, and what do you get out of it?
Yeah.
So as a matter, oh, sorry, you don't want to look at these. I was just trying to get, I realized that there was something worth showing from that perspective. Hang on, I got to get out of this because otherwise you'll see more than you should.
You got dropped off hopping anyway, so you can
Okay.
do a little more.
Okay.
Yes, it's free form.
So this ease of use is always a fascinating thing. This is an old demo from Kitty Hawk. The top is 230 bootable nodes sitting inside half a rack, a quarter rack of a Blue Gene. Actually, let me go to the next one. And yet, is this FS demo? Okay. And today, how many thousands and thousands of pieces of software and complex layers does it take to build a container-based application hosted on some large stack of hardware and software? So providing one very simple scriptable interface that I can write bash scripts, I can take, so I got to figure out how I actually scroll the video. Yeah, there we go. So actually, can I do this? Okay. So all I'm going to do now is use a very simple bash script, and I have allocated a new intranet for my company inside BlueJean. It can only be accessed via the consoles, except I give you a secure connection to the consoles. There's no software on it, okay? And these scripts are going to start building out intranet. It's going to have a gateway, a file server. It's going to boot Fedora 8 in the day, running on PowerPC BlueJean node, but as if they were a utility. And then, as a matter of fact, I think this is the one. I'm just going to scrub forward. If I can figure out how to scrub forward. Okay, so as this thing is going along, it's built disks, it's built a disk factory that it can go get more nodes to create more disks out of. It creates a file system, it launches Linux instances, and then it's going to launch a distributed compiler. Now, maybe some people don't like bash scripts, and maybe that's not considered easy. But consider this was such little software, and yet I could do what we constructed now out of pure hardware in a couple hundred lines of bash script, to the point that eventually, oh, sorry, by the way, this whole interface is running. So this is a desktop, and I'm actually I'm using the programmable interface, web interface of Kitty Hawk to actually build these things. And this is just a visualizer to make my life easier. But if I scroll to the next one, yeah. So by the time this one ends, I've literally gotten an entire desktop running with distributed compilation going on, all kinds of stuff. And then we have another one where we converted the entire Kitty Hawk into a supercomputer job that I lost access, so I wasn't at IBM anymore. But I could go to Argonne, submit my HPC job, and then it exported itself out as a web service back to BU. And there we went to town then. Then we ran all kinds of math software and interactive software. But these are Fedora instances coming up, I think, I paused the video. But so again, I think this ease of use thing, as systems people, my job is to build good primitives. And if I've done my job right, then when people discover those primitives, they can see, hopefully, the value in them. As a matter of fact, I had a slide very early on, which I removed, that said, to know something about me, I like simplicity, I like aesthetics, but I also like the safety of hiding behind the fact that, look, I'm just an academic. I think those are great primitives. I'm not going to build anything else. But I think, to your point, I think it's really about the utility that we make. Anyway, any other questions? Anyone want to argue that operating systems don't matter? That's fine.
Well, thanks, Jonathan.